It's my pleasure to share with you some comments on how we might explore the nighttime equatorial electrojet with sounding rockets. And I'm going to start off with some background material on the currents in the lower ionosphere, essentially the dynamo current and the electrojet currents, and previous sounding rocket measurements of those current systems, and then use that as the springboard to talk about the nighttime electrojet. So if you're not familiar with the dynamo and electrojet, they're observed on the ground with ground-based magnetometers as seen on the right. As a function of latitude and as a function of local time, you'll see these sort of sinusoidal variations. And those all pertain to a system of currents you see on the left, the global daytime currents, where you have morning and afternoon currents, meridional, closing at the higher latitudes. But the most important current, the strongest one by far, is the equatorial electrojet. And that was first seen with ground-based magnetometers. You can sort of see that down where it says Huancayo, that arrow at the bottom. There's no sort of pointer here. It's 10 times greater than the currents you see at other latitudes. Okay, so why do we have these currents? This is basic geophysics, essentially. We have currents because there's a conducting layer all around the Earth, all latitudes, and that conducting layer exists because essentially the ionosphere has equal numbers of electrons and ions, and the ions are simply heavier than the electrons. It's just the bigger mass, and hence their gyro frequencies are lower, and their collision frequencies are higher. The ion-neutral collision frequency and the electron-neutral collision frequency are different, and those depend on the mass as well. So if you look at this sort of dotted lines on the left, the conducting layer, you can see there's a region where the ion-neutral collision frequency is higher than the ion gyro frequency. So those are collision-dominated. They can't move. They don't move easily. However, the electrons are, we call them magnetized. They're much more mobile, and the electron gyro frequency is much higher, just from the equation, and the electron neutral, and it's much higher than the electron neutral collision frequency at almost all altitudes. And hence, that's a region where currents flow. And that happens, that can be expressed in terms of mobilities and conductivities over on the right-hand side. So the strong Hall current, for example, is indicative of the large dynamo and electrojet currents. So that's everywhere. So we study these currents as part of nature. They're on other planets. We want to understand them. How do they work? So at high latitudes, we have something called the auroral electrojet. Those are really intense currents. They're driven by magnetospheric electric fields that map down. That's what EZ is after, those really strong currents. We call the auroral electrojet. At mid-latitudes, low latitudes, we call it the dynamo. It's driven by the neutral wind dynamo. It's much smaller in comparison, but it's still important, and it actually has a very large consequences that those currents generate electric fields that then map up to fill the entire ionosphere. What this talk is about, though, is something called the equatorial electrojet. That's set up right at the magnetic equator, and it's set up because there's a polarization electric field that is enhanced by something we call the Cowling conductivity. And to go through that, here's the same diagram. You can see that there's a vertical polarization field, which is set up because the ambient zonal field tries to do what's called an E cross B drift, and that drift, vertical drift, can happen because of the fact that there's a conducting layer and the electrons and ions don't drift equally because of the collision frequencies. And as a result, you'll get this polarization electric field that's set up, and that has an E cross B drift, which enhances the current by a considerable amount. And this effect only happens at the magnetic equator within 1 degree. So you get the polarization electric field is directed upward. That drives a very strong current, which is eastward, and that's essentially the electrojet. And you can go through the equations. That's essentially the Cowling conductivity at work. Now, I'm now going to give you background about rocket measurements. Sounding rockets have been exploring the equatorial electrojet really since the beginning of sounding rockets. And I make this point because After World War II, the V-2 rocket technology came over to the US. There were scientists, like everyone in this room, who got together, and they got together at APL, and they discussed, what are we going to, if we can get into space and do research, what do we want to do? And some wanted to do upper atmosphere, some wanted to look at solar spectroscopy and the UV, some wanted to look at cosmic rays, Geiger counters. And for the geospace community, one of the primary motivating research goals was to look at the Equatorial Electrojet, because this was seen in magnetometers from Huancayo to be very large. It was a big puzzle. Why? And people were thinking, could it be a conducting layer? Could there be a collision frequencies? Could this explain why we would have this huge current in the Electrojet? So as a result, magnetometers were developed. There was a test rocket from White Sands to look at the Wannerabee, to look at the, that magnetometer couldn't see the dynamo current, wasn't sensitive enough, looked at the ionosphere, and then we went down to the magnetic equator in a ship in 1949 to look at the Equatorial Electrojet. And it was that compelling. Everyone had a theory, why do we have these currents? And as a result, they saw the Equatorial Electrojet. They came up with diagrams for the whole current system. You see there in the middle. There was the magnetic signature on the ground. Those are hundreds of nanoteslas between the tick marks. And that's when they launched and they saw the Electrojet. I should point out that this was so exciting that Revell actually came up with a model of this ship. And I've actually looked for this on eBay, several $100s. I haven't used my precious grant money to go to buy one. But I just want to point out, here's a sounding rocket. And this toy was available in the 50s. And I wish my parents were still alive. I'd ask them if they got me one. Anyhow. So so that's sort of some background. NASA's had there's been all sorts of sounding rocket campaigns to look at not just the Electrojet, but other phenomena at the magnetic equator. I should really point out, it was mentioned by Lindsay yesterday about raccoons. There was also raccoons that were launched in the South Pacific to look at the Equatorial Electrojet in 1957. NASA started in 58, and it's had a number of campaigns here. And we'll talk about that in just a second. So as a result, the main one of the main objectives, again, looking at the Electrojet current, was seeing how it varied. How did it vary with the ground base, with season, with, where was it? And essentially with altitude, you can see it fits perfectly with the conducting layer. It's about 10 kilometers thick, peaks at 108 kilometers, 107. And here's some results on the left from NASA rockets. On the right is from rockets from India. And the top graph shows how the strength of the Electrojet would correlate with the ground-based magnetometer signal. Okay, now, then we wanted to understand the electric field. Remember the polarization electric field associated with this current. So we had the Brazil campaign, NASA's Guara campaign in Brazil in '94. It originally was going to be in Peru, and for political reasons that we went to Brazil. And as you can see here, we measured not just the current, but the electric field. The electric field is in the left two panels. That's the polarization, that vertical field, peaking 105 kilometers just where the current peaks. And actually, you can calculate the drift velocity, that's the far right panel, from just E over B, E cross B, and also just taking the current and dividing by the density and getting very similar results. In fact, where they differ is probably due to the neutral wind, which wasn't measured here. So we did this. I should point out, this is the first time we measured the magnetic field with a flux gate. All previous ones have been done with proton precession magnetometers. It's the only way to get the sensitivity. We had magnetometers from Mario Cunha. He built the magnetometers that went on Voyager and many other satellites. I told Mario, going to Jupiter is a great deal, but going to the Equatorial Electrojet is where we need your magnetometer. And we flew those during the Guara campaign. We also got the electric field with the aid of the ACS from Wallops, where we flipped the rocket on the side to point the spin axis with the magnetic field. And as we spun, we could get the vertical and horizontal electric fields, whereas previous, like in the Condor campaign, we didn't have that. We only got the horizontal electric field. Okay, by the way, in Guar, we also had, this is one on the bottom is a moderately driven one. The one I just showed you is on the bottom. The one on the top is a much more strongly driven event. You see the vertical electric field is like 14 millivolts per meter. The current density is up to 12 as compared to 8. And when it gets strong, that's when you turn on the two-stream waves, and you see that only in the top panel. That's a whole nother talk. I'm just saying that this is some of the physics that have to do with the current-driven system, such as the Equatorial Electrojet. You see all that structure in the electric field and density? That's also due to large-scale irregularities, kilometer-scale irregularities. Okay, now, what about the nighttime? That's what this talk is about. So I think we've done a very good job in the daytime. We can go back with neutral winds, whatever. But what's happened at nighttime? You never see the nighttime. Why? The density is so low in the ionosphere during the day, it doesn't make a signature on the ground for the current. And, but nevertheless, you're still going to have a conducting layer. So in the conducting layer, the electric field should switch directions because the ambient zonal electric field changes direction. And so now the polarization field should be pointed down. And there should be a current opposite to the daytime current, very hard to measure. So I put this actually in my thesis. And I said, we ought to go to the nighttime. Well, the nighttime's important because the HECA marker radar sees all sorts of irregularities and things. So the nighttime is one of the most interesting times. It just doesn't have a strong current. Now, another thing happened. We launched CNOPS. CNOPS was a satellite. We had the magnetometer on and electric fields. And so we analyzed the magnetometer data. And what we did was for different local time, as a function of longitude, we plotted the strength of the magnetic field. And this blue line, there's no pointer here, but this blue line is between 11 and 13 local time. That's the Equatorial Electrojet. That's the strong current that we've just been talking about. But notice, at night, there seems to be some sort of organization of the currents. And they're not so small after all. So what we did was we put together the daytime and the nighttime. This is for early morning, 3 to 5 local time, and it's very seasonal. And you can see there's the nighttime Electrojet. And in fact, the other component, the delta B up component, changes between the blue and the yellow on the top, right at the magnetic equator. Same way on the nighttime, it changes the opposite way, reinforcing our interpretation that the nighttime Electrojet has a current that's measurable and important. In fact, you know, I asked my colleagues from Germany who work with the CHAMP data, now the swarm data, I said, do you ever see the nighttime Electrojet? Claudia Stoller says, oh, we just don't look at night. We just look from 6 a.m. to 6 p.m. So I got on a plane, I flew out to see Herman Lohr. I say, the nighttime Electrojet is there. And he said, yeah, maybe you're right. And little did I know, a year later, he published this with CHAMP data. But it's really something I've shown at a lot of meetings and trying to get people's attention that we can measure the nighttime Electrojet with satellites. Okay, now back to rockets. So here's how we do it in the daytime. This is with the daytime with the proton precession magnet, a scalar. So when you have a scalar, you don't have any vector information, but you can see that as you cross, if you look at the top panel, as you cross the Electrojet current, you're going to see a delta B change. And that's how all the previous ones before Fluxgate saw how the Electrojet was ascertained. And so here it is from one of Nelson Maynard's rockets from the Antarctic campaign in 1975. It turns out NASA had all these rockets that were flown in 1964. And they had all during the daytime. They had one nighttime rockets in this paper by Davis et al. He was a Goddard researcher. And in fact, there was this ship that had 14 Electrojet rockets from NASA and AFRL. And there it is. There's the nighttime Electrojet going the other direction. That's, I think, just buried in this old JGR paper. So that was very heartening. So what we want to do is we want to measure that current along with and see if the polarization electric field has changed direction, and then look at the consequences as far as the electrodynamics and the instabilities. So now I mentioned HECA marker. This is some data from HECA marker, 3 different days here just showing you this is what's called backscatter. The radar sends up a pulse and then looks at the return, and then does it as a function of altitude. And where you see, all these are in the Electrojet region. And as you can see, first of all, this is called backscatter echoes. The echoes seem to be bifurcated between a lower level and a higher level. So why is that? Is it a neutral wind effect or a density effect? But you can see all the structure, the large scale waves you see on the bottom panel in the upper altitudes between 105 and 120 kilometers. Those are probably large scale gradient drift waves. So there's a tremendous complex electrodynamics associated with the nighttime Electrojet. Oh, by the way, this is some data from sunset. I was talking yesterday about the vortex. We believe this is a signature of a large-scale structure between daytime and nighttime, which can actually produce this very large backscatter. There have been rockets at night. This is one from India. You can see the plasma density is about is typically over 10 to the fifth. It's reduced over by two orders of magnitude at 105 kilometers. You see all the structure on the right-hand side. So there have been some rockets at night, but we've never measured the current and the polarization field and the winds at the same time. One other note about Hikamarka. Hikamarka has decades of history where people have been looking at backscatter echoes and trying to understand them. And one of the puzzling asymmetries reported by our Hikamarka is funded by NSF. This is researchers who have been going down, and they're just puzzled. Why is they see these what looks like this sort of saturated phase velocity? Each altitude here is a strip of Doppler spectra from the radar, and you still see those sort of flat tops. And gee, that's funny. So there's all these theories about is there some mechanism where the instability is saturating on its own. Farley-Bunemans, these would be two-stream waves. Well, it turns out during the Condor campaign, we launched in the daytime, and there was also this square tops, but they were going the other way. This is the asymmetry. It's a little hard to see here without blowing it up. But we measured with the rocket that the electric fields themselves were saturated. And this is the zonal component. So the zonal component would give you the vertical drift. And this is a complete puzzle. And I actually showed this during my thesis defense. And the committee said, why should they be square? And before I could answer, my advisors jumped up. He said, we observed them, we observed them. And this is sounding rocket, this is NASA rocket. And this same square waves we would anticipate would also be present at night. And at night, the wavelengths are much longer. That's why it was easier to see on this previous panel. And the reason that gets square is you want to keep the current continuity del dot J 0. And you can go through the equation and you can see that the electric field is the agent that keeps that current from overshooting, so to speak. Now, I now want to, in my final minutes here, talk about Project Cielo and the opportunity, which is, I think, an ideal opportunity to address these long-sought questions. We know the Peru campaign is on hold or on pause, but we want to keep it alive, and this is something which was part of the white paper, and we're hoping it could help motivate keeping a future rocket program going. I should point out that we had a nighttime rocket in Guar in 1994. There was a NASA failure of a rocket. It wasn't our fault, it was a NASA fault. So the rocket we had intended to launch at night, we couldn't. Then we proposed 2 rockets doing the nighttime Electrojet in 2000, 2004. Those were approved along with other researchers. That was for for Peru. And then that entire campaign got switched to Kwajalein. And we explained we weren't going to be able to do the same science, but there were memos back and forth, and so we still had the Kwajalein campaign. But anyhow, the idea is from Puerto Lobos, we would launch in the nighttime Electrojet. Some of our science questions are looking at the large-scale electrodynamics, looking at the vertical DC electric field and how that compares with the current. Does everything flip as we do in our diagrams and our cartoons? And does it obey the Cowling conductivity predictions? We want to look at the neutral wind effects on the nighttime electrodynamics. And in particular, how does that influence the DC electric field? And does the neutral wind, which typically shows Kelvin-Helmholtz structure in the dynamo, in the sporadic E, do we see that same sort of structure at the Equatorial Electrojet? And if so, how does that affect the electric field? And then also, what is the role of plasma instabilities in the nighttime electrojet, both the large scale and also the two-stream waves, which we would predict would be there for sufficiently large electric fields. All the established instruments are on hand. Here's, I just give the electric fields, which is something we built with our lab and which we flew in from Brazil. And then the other instruments, everything, we don't have to invent anything. These are all tried and true instruments. We have a traceability matrix, all the required performance is right there. I just want to end by saying the Electrojet can be expected to be there on other planets, particularly planets with a partially ionized upper atmosphere and dipole magnetic field. There are papers on this. This is one for Jupiter. And so it's really a fundamental part of our planet. Just to conclude, I won't read all this, but Electrojet is fundamental. We've done great. Sounding rockets have exposed the mechanisms of the daytime Electrojet, how that works. We want to do the same for the nighttime, particularly because of all the predictions by theories that the current should reverse direction along with the polarization field. We expect these large-scale structures. We don't have any idea of how the neutral wind will enter into the picture, but we expect some winds, and we expect those would complete the electrodynamics picture. You carry out the rocket experiments in conjunction with the ground-based experiments, such as the HECA marker radar. Other planets are presumed to have electrojets, and so sounding rocket measurements in the nighttime electrojet will help provide this basic understanding of these fundamental processes. Thank you.